close enough, then you can find as long as the projection is a reasonable projection, then the difference between the smooth function and its projection is bounded by h to the power k plus 1. K is the polynomial degree. So this part is going to be fine. So what is important is to prove this part, the CU and the CV. But we already mentioned that the CU and the CV are indeed in the finite element space. So what we could not do here, we could do when we take the test functions this way. So let us now erase what is here. And let us now take, so we basically try to mimic what is done in the stability proof. We take Z to be, instead of UH, we take it to be CU, and we take W to be CV. Then we start to write down the equality here, these two equalities, when we replace Z by CU, and we replace W by CV, and also we replace EU by CU minus eta U, CV minus eta V. So what we would get is that we have two parts, right? One part involves C, the other part involves eta. The part which involves C is very much like what is happening here. So basically, the part which involves C, you can basically copy down from here. So it would be C sub V squared dx plus ij, let's see, UH is replaced by EU, which is CU, eta U, CU, CV sub x dx minus UHVH, so CU, CV, minus J plus half plus CU minus CV plus J minus half. So this is this part plus this part. Ij is CU sub T times CU dx plus integration CV CU sub x dx minus CV plus CU minus J plus half plus CV plus CU plus J minus half. So this left-hand side, I'm basically copying down these two lines. Whenever I see VH, I replace it by CV. Whenever I see UH, I replace it by CU, right? Because the equalities are identically the same. So I'm putting in EU, which has CU, and the eta U, the C part, is identical to what we get in the stability proof. So this is the left-hand side. The right-hand side contains eta, right? So the right-hand side is basically similar to what we have there, but then it has eta in it. So basically we have, let's see, what do we have? We have eta V, right? And W is going to be, so what did I do? W is CV. Yes. Plus Ij eta U CV sub x dx minus eta U minus CV minus J plus half plus eta U minus CV plus J minus half plus ij, this would be eta u sub t cu dx plus eta v cu sub x dx minus eta v plus cu minus j plus half plus eta v plus cu plus j minus half. Apologize for so many things. Basically, what I'm trying to do is that I'm trying to replace EU equals to cu minus eta u. I'm trying to group all the cu terms on the left and group all the eta u terms on the right. Comes pretty long, but this long thing has a very nice structure because what we see on the left-hand side very long thing. It's a very nice structure. What we have on the left-hand side is exactly like in the stability proof. So you get this, right? So the left-hand side becomes 1/2 ddt after summation. Sorry, the left-hand side after summation becomes 1/2 ddt of 0 to 1 of cu. This is cu squared dx plus 0 to 1 of cuv squared dx. So the left-hand side is very, very nice. Now, how about the right-hand side? The right-hand side contains etas combined with c's. Now, what was the strategy yesterday? The strategy yesterday is that we still have freedoms that we have not used. The freedom is that how do we define the projection P and Q? So the guiding principle for designing those P and Q is that to kill as many terms on the right-hand side as possible, right? Possibly kill all of them, but that's usually not possible. So kill as many of them. First, kill the ones you dislike the most. Usually, the things you dislike the most are the terms on the boundary. Because the boundary terms, when you want to estimate, if they are not 0, if you want to estimate them, you get usually lots of factors. If you can kill them, then first kill them. So let me try to define my P to be such that P of u, so let me write down the proof here. Not the proof, the definition of P. So let me say P of u minus u and j plus half is 0. Let me put this as one condition. So in other words, this we have seen before yesterday. Color case at one point. If that is the case, then eta of u, which is u minus pu, evaluated at the minus j plus half, would be 0. So these two terms would disappear, right? If I define it that way. All right. So by the same token, if I define Q to be collocating in the other way, if plus half or minus half doesn't matter. If QV minus V and J minus half plus for every J is 0, then that would take care of eta V, which is V minus QV, evaluated at J plus half plus and J minus half plus. So these two terms, right? Then I can further, I have used only one condition. So the remaining condition would be that Ij Pu minus u times any function phi is 0 for phi belonging to polynomials of degree this time. I can only require it to be orthogonal to polynomials of degree k minus 1 because I have already used up one condition. So orthogonal to polynomial of degree k minus 1. Same thing here. For any same phi. So this combines two letters. So P and Q are actually not the same projection. So they are similar, but one of them collocates at the right end, the other collocates at the left end. So if I have these two conditions, then this term will be 0. This is because eta u is u minus pu, and the Kc v sub x, Kc v itself is a polynomial of degree k. Kc v is in the space, right? Polynomial of degree k. Take one derivative, it's a polynomial of degree k minus 1. But then this guy is orthogonal to every polynomial of degree k minus 1 by definition. So this term is going to be 0. Same token, this term is going to 0. These two terms survive. Fortunately, they survive. So you always have to have something, right, survive. So the right hand side has only two terms which survives. Okay. This time, I guess let me just be sloppy here. Just use AB is less than half A squared plus B squared. A times B is less than half A squared plus B squared. So this would be a summation. Sorry. There's no x derivative, so I can sum. So let me just use it to be half of eta v squared plus the cv squared dx. Yeah. Plus eta u t squared 0 to 1 plus Cu squared. Yes. So we just use A times B is less than A squared, half A squared plus B squared. So then this is less than or equal to this. We then have it's basically done. So we then have half of d dt of the Cu squared plus this is Cv squared, but there is another half Cv squared here, so that is up one of them. So it's 0 to 1 Cv tau squared b tau is less than or equal to these guys are going to be okay. These etas, right? Because we are using CLH. We can put the t derivative there, it won't change anything. So you will have ch to the k plus 2k plus 2, because it's squared, plus there's only one remaining term which survives, which is half of the cu squared. That survives. So then, the only difference between now and yesterday is that you also have this thing on the right, but you have a ddt of this thing on the left. Then you can use ground law. You can then get the final result that the C of u at t plus 0 to 1, maybe 1 with 1 half.
So the time integral should not be there on the left hand side.
What?
On the left hand side, it's a d tau term, so the integral which is there. Just the second last line you wrote. Half dt, but just about that. It's just about that you can.
First term.
The first.
The first term.
The first term?
First term is
No,
that inequality.
This term?
Next one.
This term?
Next line. Next line.
Next line?
This time.
The first term.
This is the time integral.
There's no time, yeah, because I have, sorry. You are right. I have not integrated yet. I'm sorry. I have not integrated here yet, yeah. Oh, yeah, you get this thing. So basically, with this and with ground wall, you would get basically here you have the is less than CH to the 2K plus 2. Yes, this C, unfortunately, with this proof, the C grows exponentially. Groundwater, I use groundwater. C grows exponentially with time. Remember, yesterday we were able to get C growing only linearly in time. But that's technicality, so you can probably do better. And then you control this C a little bit better. But the important thing is that we control both the derivative, we control both the L2 norm of the solution and the space-time L2 norm of derivative by the optimal order. So this is a little bit like a mixed method, right? The mixed method is able, in finite elements, is able to compute both the solution and the derivative to k plus 1's order accuracy. And here we also can control both the solution and the derivative to k plus 1's optimal k plus 1's order accuracy. And also this is better than mixed method because this is a local DG, which means that the variable v, which is an auxiliary variable, can be locally eliminated, locally computed from u. So in the explicit time matching, you only have to store u, you only have to have u as a global variable. The v would be a local guy computed from local polynomials of u, compute, use, throw away. So you don't have to store this v global. Okay, so this is the proof, error estimates. This error estimates can be generalized to nonlinear convection diffusion equations. So stability can be generalized to nonlinear convection diffusion equations, and this error estimate can be generalized to nonlinear convection diffusion equations. Again, assuming the solution is smooth. If the solution is not smooth, this proof will not go through, so you have to do something else, much more complicated. I would like to emphasize that this LDG is just one of the many available DG methods for solving diffusion equations. It's not the only one. So there are other methods called internal penalty. Within internal penalty, there are also these differences between symmetric internal penalty methods and non-symmetric internal penalty methods. They have their relative advantages and disadvantages. And there are also other, say, for example, ultra-weak discontinuous developing methods. So there are many other choices of DG methods for diffusion equations. This is because diffusion equation has an extra derivative, so that provides many room for you to do things differently, right? So there are many different DG methods, and I should not claim one method is better than the other. They all have their relative advantages and disadvantages. So if you are going to use in applications a DG method for solving convection diffusion, depending on your particular application, you might want to pick one or the other available DG methods. So because of the time constraint, I will not explain in detail the other DG methods, but you can see them from the literature. There are many discussions, many papers on these things. Rather, I would use the remaining a little bit of time to explain what happens to third order PDEs, which are the so-called KDV type PDEs, or water waves. Because it's a mathematical induction, right? We have to, the order of the PDE, we have done 1, which is hyperbolic, 2, which is convection diffusion. We are going to do 3. So once we have done 1, 2, 3, then you know how to do to infinity. You apply induction. So let's try to do 3. Okay. So the very famous KDV equation is, I don't remember, maybe it's a 3 here. This is the KDV equation. So in general, the generalized KDV equation is this. Of course, you can have a coefficient sitting here. So the important thing is that it has 3 derivatives rather than 2. So of course, there are also other PDEs from applications for which this third derivative is also nonlinear, just like nonlinear combined diffusion. PDE is the leading term. Third order derivative term is linear, but you could also have nonlinear. So again, in order to design a DG method for this, let's look at the simplest situation, which is right dropping this. This is not going to cause us trouble because we know how to handle it already. So now let's look at the simplest prototype equation, which is ut equals to u triple x with an initial condition. So let's try to design a DG method to solve this equation. Let us try to again concentrate on LDG. So the idea of introduce auxiliary variables and then introduce a system of first order PDEs rather than a scalar PDE of very high order, and then use DG method on it. So we introduce now 2 variables. So ux equals to p, and px equals to q. Then ut minus qx equals to 0. How about that? Right? So we have introduced the 2 auxiliary variables, p and q. So p is ux, q is essentially uxx. And then here we have ut minus qx is 0. So this system is now formally a first order system. So we can formally write down DG scheme approximating this system. So just repeat what we did for the field equation. We are trying to design a DG scheme for the third order PDE. So we just write down the scheme 3 times, right? So the biggest challenge is to find enough letters. So we want to find UH, PH, QH, all of them in VH, such that for any test functions, we have V, W, Z. Enough. In VH, we have, okay, the first equation is P. So Ij P times V dx. I do integration by parts here, so it's plus Ij U times, this is TH, UH times V sub x dx minus U hat J plus half V of J plus half minus plus U hat J minus half V of J minus half plus equals to 0. This is the first scheme for P, and the other one for Q, very similar. So Q times W dx, QH, plus Ij PH times W sub x dx minus P hat J plus half, W J plus half minus plus P hat J minus half, W J minus half plus equals to 0. And finally, we have this equation, which is like Ij UH, this time you have some T times Z dx, plus Ij, this time you have Q here, QH times Z sub x dx, minus Q hat J plus half, Z of J plus half minus, plus Q hat J minus half, Z of J minus half plus equals to 0. So you just write down the scheme for conservation laws 3 times, each one for approximately one of them. The only difference is that there's no sub t here, there's no sub t here, so it's not really a conservation law, but we formally write down the scheme. Now, in order to really finishing designing the scheme, you have to specify what these hats are, right? So these are the numerical fluxes These are the crucial components of the DT scheme, because if you do not give them correct definitions, then you end up with a scheme which is either not unstable or inaccurate or both. Right? So you would like to find good choices of those numerical fluxes so that the resulting scheme is a good one, stable, it's optimal convergence possible. Right? Okay, so what would be the guiding principle here? What would because you see that for the first order PDE, hyperbolic, people already told us that finite difference, finite element, finite volume, people already told us that the guiding principle is upwinding. We have the so-called monotone fluxes, we can use them. So that's the first order. Second order PDE, heat equation, we do not know what we should use, but then there is some symmetry, right? So the information propagates in all directions. So we could use average, we could use alternating. Alternating, actually, if you think about it, is also symmetry. Because if you use left and right, you eliminate the middle guy, and everything becomes more balanced. Right? One uses left, one uses the right. After eliminating the middle guy, as a matter of fact, for the P0 case, after eliminating the first guy, you get a perfectly symmetric three-point difference, right? So that's the guiding principle. So what would be the guiding principle here? Third order PDE. So I don't know if you have studied, some of you might have studied the PDE theory of third order PDEs. These are called dispersive wave equations. Since they are wave equations, they again have a preferred direction. I would suggest that you put in a simple mode, right, as the initial condition, and then you figure out whether the solution is a moving wave. So whether the solution is x plus t or x minus t, moving wave. For this equation, if you take some t, it is cosine x plus t. If you take 3x derivatives, it's cosine minus sine minus cosine.
Oh,
no good.
minus t, yeah.
This is better. Then I have minus here. Then I have, yeah. Perfect. So this means the information is actually flowing from left to right. Right? So the information is flowing from left to right. That means there is some upwinding that I should use. In other words, I should use a bit more information from my left than from my right, because the wave is coming this way, right? It's from this point of view, it is a little bit like a hyperbolic. Don't you think so? It's not like heat equation. Heat equation information propagates in all directions equally. Here, okay, it's a preferred direction. So I should use more information on the left. But I have 3 fluxes to determine. So I could say, if I want to use more information on my left, I have 2 choices. Either I use 2 pieces of information on my left and 1 on my right. So this is to prefer the left, but not completely rely on the left. Right? 2 and 1. The other is very extreme. I use all 3 pieces of information on my left. So make a guess which one would be better. I don't know. In India, it's what people are more composed, right? So don't go to the extreme, right? Too slowly. So just take 2 from the left. Even if this is a poor guy, I mean, you don't like it that much, but use it a bit. So use more of what you like, but don't just eat 1 food, right? So the guess is that you should take 2 from the left and 1 from the right. Of course, this is just waving hand. You should try first to put all 3 from the left, and then try to analyze the stability. You find, whoops, the scheme is not stable. So if you go too extreme, then chances are it's unstable. Have to be a bit more balanced. So if you take 2 pieces from the left and 1 from the right, you also have the choices of which one to take from the right. Or rather, which tool to take? It's the same question, right? Which tool to take from the left, from the wind direction? This one, again, this waving hand kind of argument will not tell you the answer. So this you would have to say, do trial and error, I would say, right? Try and see what would work. I remember that by that time I was giving this project to my former PhD student, Julian. So she did it after 1 week. She came back and said, oh yeah, it works. What is it? So basically the guiding principle turns out to be that you have three things, right? You have U, P, and Q. This P is approximately U sub x, and Q is approximately U sub xx. Right? P is Ux, Q is Uxx. It turns out that it is crucial, so this you should memorize, it is crucial to do upwinding for the middle guy. The middle guy is the most important, right? Usually that's true, right? The middle guy is the most important. Both ends. So this guy must be taken from the upwind side. In other words, in this case, the wind direction is from the left. Then this P hat has to be taken to the this P hat has to be taken from the left, the upwind side. Then these two guys, the first, the function itself and the second derivative, these two can be taken alternatively. So this, they have some elliptic component in there, a parabolic component. So this U and this Q can be taken in an alternative fashion. So you can take U minus Q plus, you can also take U plus Q minus. So let's take one of them. So U hat J plus half equals to U minus J plus half, and Q hat J plus half equals to Q plus J plus half. Or you can take the other way. So you can take plus J minus J. Both of them will work. So this is the guiding principle. The middle guy determined by upwinding, and then this group to alternatively. So this goes, like I said, this is mathematical induction, right? So once you know how to do third order, you know how to do fifth order. Because fifth order, the middle guy is still upwinding. And this group, you alternate, and this outer group, you also alternate. Will work. Okay, so that's the choice. So let us do. Okay, so let us try to justify my claim. In other words, let me try to prove stability. I did say the last proof was the last one, but I attempted to have time to give another proof. So let me try to prove stability of this scheme with this choice of numerical fluxes. So you remember the proof, the idea is to take the test functions suitably. You see, all this the DG proof is to utilize the fact that the equality holds for all test functions. So then in a specific proof, it's your job to choose the suitable test function, right? If you choose the wrong test function, you will not be able to prove your result. Maybe you proved something else, or you proved nothing. So it is important to choose the correct test functions. So how do you get that? Let me try to guide you through the stability. So what is the idea? Well, stability, first of all, what kind of stability are you looking for? This is a third order PDE with ut equals to uxxx. Then the stability proof is basically L2. Because for this PDE, you can show that the L2 norm is conserved. For us, of course, we want to prove that the numerical L2 norm is less than or equal to the initial L2 norm, so that will be stability. So you want to reach L2 norm. So in order to reach L2 norm, I at least know what Z should be. I should take Z to be UH, because that it will provide me exactly the ddt of UH squared, right? So that is the quantity I want. And I will worry about the remaining things later. So first thing first, right? I want to get my term that I want first. So I already know Z should be taken as UH. So then I will get the following. I will get Ij UH sub T times UH dx plus Ij QH UH sub X dx minus, let me already plug this in. So it's QH plus J plus half UH minus J plus half plus QH plus J minus half UH plus J minus half equals to 0. So this is the equality I get, this third equality. When I take Z to be UH, I get this. So far so good. Now this term is already what I want. Now in this stability proof, you know, the most important thing is to get rid of those integrals, because these integrals are always troublesome. If everything goes to the boundary, then maybe the fluxes will take care of that, right? Will either all these boundary terms will cancel, or the boundary terms will combine after summation to some positive term. That would be nice. So I want to get rid of this. In order to get rid of this, the best way is to get a perfect derivative inside. So perfect derivative integrated over the interval, I get contributions on the boundary. So this is QH times UH plus. So I need another term, which is QHX times UH. Then I combine these two, I will get a perfect derivative. So where do I get it? I should be able to get it from one of the top guys, right? So it should be from the first guy, because the first guy already have UH. So then if I take V to be QH, in the first equation, I would be able to get this. So I would get basically Ij PH QH dx plus Ij UH QHX dx minus U hat. Let me already put it in. U hat is UH minus J plus half QH minus J plus half plus UH minus J minus half QH plus J minus half equals to 0. So I already have taken care of this. This will go to the boundary. But then I have this term, which I don't like. It's again something integral with no sign. So I do want to get rid of it. So in other words, I want a term which is minus of this thing. And that can only come from the second equation. Second equation does have QH. So if I take W to be minus PH, in the second equation, I would get exactly the opposite of this. QH, PH, dx, so that would cancel this. It's very nice. But of course, I will get something else. Let's see what that something else is with a minus sign. Ij, the PHX dx, but that's okay because this is again a perfect derivative. You will go to the boundary. I don't know if it's okay, but at least everything will go to the boundary, which is nice. I will worry about the boundary later. So minus plus p hat. Let me put p hat in already, which is p minus ph minus J plus half ph minus J plus half minus pH minus J minus half pH plus J minus half equals to 0. So I have three equalities by taking specific test functions this way. And I have motivated you on how they are chosen. They are sequentially chosen one by one, so that I first get my desired quantity, which is this guy. Then I have some trouble terms. Trouble terms, I want to get rid of them in a specific way. making it the perfect derivative that determines this choice, and this I want to get rid of and get this choice, and so on. Okay, now let me then sum them up and see what happens. See what happens. So I will have the very good term, which is the first term here. One half ddt of ij of uh squared dx. This is the best term. Then let's see, what do I have? These two terms will cancel. I will have this term which goes to the boundary. So it is plus QHPH, right? No, QHUH. QHUH evaluated at j plus half from minus, right? Recall when you are performing integration in the cell, on the boundary, you achieve values from inside. So it's minus here and plus here. So that takes care of these two terms. Then there's this term, which is 1/2 of pH square of sub x. So that gives me 1/2 of pH square j plus half minus plus 1/2 pH squared j minus half plus. So that is from here. And then I have also 6 boundary terms. I have a lot of boundary terms, right? So let me write down all these 6 guys. So it's QH plus UH minus J plus half plus QH plus UH plus J minus half minus UH minus QH minus J plus half plus UH minus QH plus J minus half, right? Plus pH squared minus J plus half minus pH plus J minus half. Alright? Yeah, equals 0. Too many things. Don't worry, they will behave. So the first term is what I want. The remaining terms, I would want them either to completely go away or provide some positive contribution after summation. So let me first sum, right? Summation over j. Then the first term becomes what I want. First term is what I want. The remaining terms, because after summation, you can forget about j plus half, j minus half, because everybody comes to the same point, right? Summation, everybody is, let's say, periodic boundary condition. So what do I have? So if I forget about the lower indices, then there are a lot of terms which will go away, no? For example, this and this will go away. They are already going away, even if I don't take care of the index difference, right? Anything else which will go away?
Second is QH plus QH plus.
The second
And this.
and this, right? Yeah, they are already the same, even without index difference. I think these two things are the same if you take care of the index difference. because it's J plus half and J minus half, but otherwise it's U minus Q plus, right? And with positive they are negative here. So after summation, these two terms, they don't cancel, but after summation they will cancel. Anything else who could cancel? Unfortunately, no. Well, at least you can not cancel, but you can combine this with this to get a half, right, of this. But then that's it. I think that's it, right? So then let's put everything to the same location. So there is a summation of J. There are three terms left. 1/2. Actually, let's put 1/2 out. So three terms. pH minus squared. That's this guy. And pH plus squared. That's this guy. And minus 2, because I put out 1/2, so there's a 2 here. pH minus pH plus. So you are left with this guy. But this is perfect, right? So this is basically pH plus minus pH minus squared. Which means this quantity plus some positive quantity is equal to 0. This exactly means stability, right? So this implies that this quantity itself, ddt of 0 to 1, UH squared, dx is less than or equal to 0. So this is what we want, stability. We also know how much dissipation we have. The dissipation is proportional to this jump of P. So pH jump, right? Jump squared. So if you have a bigger jump, then it gets penalized more, then the energy decays more. So if you have a smaller jump, then if you have no jump, then this term has no contribution, then the energy would be closely to conserved. More jump means the energy is more conserved. So this is how you prove stability, right? So you can see that this choice of numerical flux is quite nice. It's very natural. First of all, it's a pattern to follow. You use the middle guy is upwind guided, and the other pair you do alternating, and then it turns out that you have a very nice stability result for the energy. Now, how about accuracy? Then I cannot, even if I want, I would not be able to. Even if I wanted, I would not be able to give you the proof, because it turns out that this scheme is optimally convergent. So the L2 norm is indeed h to the k plus 1. Not only the L2 norm, but also you can control the derivatives. However, the proof is much, much more involved. So if you follow what I described by mathematical induction, what I described for the hyperbolic case, for the heat equation case, you apply the same technique like J.N. did, same technique to this scheme, trying to design projections and so on, and try to balance terms, trying to get proof for accuracy, you lose half an order. So in the original paper of J.N. and myself in Science Journal in Microanalysis, when this scheme first appeared, we have the proof for accuracy, but that was k plus half. But of course, you go to the computer, you run, you find out perfectly k plus 1. So it's a problem of the proof. It is not fact. We really lost this half order. It took us several years that Yan Xu and myself proved only a couple of years ago, so very recent, that we were able to utilize not only the scheme, but also take the this is a semi-described scheme, take the t derivative of the scheme, and taking different test functions and so on, we find out that we can not only control the function, we can also control the derivative. We can also get the stability for QH and pH. See, the trouble is, in the PDE, stability here does not involve the derivative. It's not like the heat equation that the stability already involves gaining regularity or gaining derivative is controlled by the solution itself. This is not true for wave equation. For wave equation, if you want to control the derivative here, u sub x. If you want to control this, you would have to use u sub x initially. In other words, the type of stability you would like to prove is that the pH and the QH also individually can be controlled by their initial conditions. This is very different from the proof for hyperbolic case for which you don't need the derivative at all, or for the heat equation case for which you do need the derivative, but the derivative can be controlled by the solution. Here, the derivative can only be controlled by the derivative, hence the proof is much, much more involved. But at the end of the day, we can claim that, so this is the result of Yan Xu and myself in Science Journal Numerical Analysis a couple of years ago. That U minus UH in L2 is almost optimally convergent. So actually we prove a bit more than that, but yeah, this is good enough. Okay. So we don't lose accuracy. So this particular choice of numerical fluxes is really nice. So you can prove, of course, once you figure out how to prove it for the third derivative case, then over there we tried 5, 7, 9, 11, 13. I don't remember where we stopped. You can do it for every odd. Okay, same type. So, but the proof is a bit different than which I will not be able to cover. So let me use the remaining just a few minutes to summarize a little bit about the DG methods. So in this very short course, we are describing first hyperbolic problems. What would be the discontinuous Galerkin method? I would emphasize that I would say the success of DG method relied heavily on the choice of numerical flux, right? For the hyperbolic case, you see that the stability relied heavily on the monotonicity of the schemes. So you have also seen that in the heat equation case, if you don't do it right, you get a wrong scheme, which is unstable, right? So you have to do it right. What do you mean right? Again, it will be the choice of numerical fluxes. When this LDG things is formulated, it's again crucial to choose the numerical fluxes correctly. For example, it turns out that this alternating choice is doing a good job. Alternating choice gives you both stability and optimal order of convergence. I did not mention induction at that time, but the induction goes here also. So for all even order guys, so we did the second order, right? Heat equation. Suppose you have biharmonic, which is a fourth order PDE. Then you mimic what you did the LDG for heat equation. You have 4 guys. You have the solution and 3 auxiliary variables. Again, you pair them up, and you do alternating on each pair. You pair them up, you do alternating, and then you get the same result: stability and optimal order convergence. You can do 6. I don't know what is the 6th order PDE called. The 4th order is called biharmonic. 6th order is called biharmonic. Something like that. So you can do 6, 8, if you have such PDEs. So you know that's pattern. So that's like induction. And all the other guys here, we showed you how to do 3rd order. By the way, this particular scheme can be applied to the KdV and also to nonlinear, very nonlinear type KdV type equations for which the 3rd order derivative is nonlinear. You can do the same thing. You can gain stability, and you do exactly the same trick as you do here. So that's very nice. So once you know how to do 3rd order, again you know how to do 5th order, 7th order, and so on, because we have spelled out the guiding principle, right? The middle guy is always upwinding, and then you pair the remaining guys in an alternating fashion, and this should work. But of course, you have to prove this in each individual case. First prove stability, and then try to prove error estimates. So by summarizing this, we have basically covered time-dependent I think, right? Most time-dependent PDEs. So if you have a time-dependent PDE, you chances are, if there is a stability, I mean, well-Poisson's result for the PD itself, usually you do. You see, all these PDEs, they don't drop from the sky. They are coming from some physics. And there's always, I should not say always, there's usually some quantity called energy, or called entropy, or called something, which is a positive quantity, which does not grow in time. Either decays in time or keeps constant in time. This energy could be a complicated function of the solution, but it's usually a positive quantity. So as long as you have such a thing, the first thing you should try is to design your DG scheme with suitable choice of numerical fluxes so that your numerical scheme obeys the same boundedness for the energy, for that physical energy. So this is first thing you try. And if you can achieve that, then you move on to prove, say, error estimates. Usually that will not be too hard. Stability is the key. Because if you cannot, stability guides you how to design the flux. So if you don't have stability, then it's very shaky, right? The scheme, you don't want to use it because it could be unstable. So when you are facing a new PDE, so this would be the strategy. So you first ask the people or derive it yourself when the PDE has some L2 norm or some energy which is bounded. This decays in time. Ask people where this PDE comes from physics. So if in physics, there must be some energy, no? The energy. So try to derive that energy which decays in time. And then sit down and see what type of PDE it is, and then try to use all these tricks to see if you can design the fluxes so that you get same proof on your scheme. And then go to the computer, and then prove error estimates, and then write a paper. Alright? Yes, sir. Yes.
For example, for convection diffusion equations, and let's say for second order accurate, what would be the computational complexity of this DG compared to finite volume method or finite difference method?
Okay. If you use explicit in time, this is a finite difference. But like I mentioned, right, it is some kind of finite difference method. So very comparable. As to finite volume involves some reconstruction. And here you don't have reconstruction, so that's the plus. But the negative side, of course, is a big storage. You have to store the whole polynomial.
And for that heat equations, what about the positivity of the diffusive terms?
Okay, this, so yesterday we proved positivity for DG scheme with this trick, right? Unfortunately, I have to report that if you want to do it for convection diffusion, then we know how to do it only for P1. We have not figured out how to do the same thing for PK with K bigger than 1. Yes.
Yeah, in the heat equation, you replace the Laplacian by some other operator, say P Laplacian.
Yeah.
Does it work?
Yeah, it works. As long as you have this energy, usually you do. Yeah. So you can have nonlinear, very nonlinear thing. As long as this coefficient A, it's like this AU, right? In 2D, this A is a matrix.
A depends on the gradient. The P Laplace case, the A depends on the gradient.
A depends on the gradient. A depends on this, okay?
Yeah.
Do you have an energy estimate? Do you have an energy
It's
estimate?
yes, because it is a maximal monotone operator.
Okay.
So it can.
It's
No, no,
elliptic.
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 Yeah, it is a maximal monotone.
Okay. Then
So
yeah.
you do get the
Yeah.
energies.
Should be okay. Should be okay. Yeah, should be okay. Because the thing is that if you have physically energy bound, then this trick. So it depends on how you prove that bound. Usually you multiply the PD by something and integrate it by parts, right? So you try to make this thing in the DG level. So what you would get is that usually you can do everything formally the same way. You end up with a lot of boundary terms because for the PDE you don't have boundary term. It's a continuous thing. Here, if you do the same trick, integration by parts and so on, you end up with a lot of interface terms. And then this will be the role of the numerical flux that should help to kill all these terms or make them positive. Any other questions? If not, so we are just on time, right? Very sharp. Yes, you want to see the level how that is working. PDT of the function. Usually, if you multiply the CD by a suitable function integrate, then you get that. Usually, as long as it goes on that way, you have a whole function. Because this is what each does. It's the most important because this guides you how to design the class. Without this, you are never sure whether